Good morning, and now we will start the second part of our previous course, Advanced PDE Part 2. In Part 1 of this course, we have covered basically distribution theory and Sobolev spaces, and in Part 2 we want to use the Sobolev spaces and distributions which were studied in Part 1 to understand PDE problems. Especially we will restrict to linear partial differential equations, namely elliptic, parabolic and hyperbolic. So, in the next 20 lectures, namely 40 hours, we will be covering these topics, especially the weak formulation of elliptic PDE and then the formulation of evolution equations including heat equation, wave equation and then Schrodinger equation and see some other equations if possible. So, I begin with giving a brief overview of this course, and then we start our lectures on this course. So, we begin by a review of this course, especially review of Sobolev spaces, not distribution theory. Distribution theory is used to study Sobolev spaces, maybe 3 lectures. 3 lectures means 1.5 hours. Okay, that is what you will do in the first thing. After the review lectures, we could not finish certain important things from the Sobolev spaces, especially certain inequalities, which is important to study the course inequalities. And we also studied little more about embedding theorems. We have stated some embedding theorems, and we will discuss little more about embedding theorems, and basically embedding theorems are some review theorem. This also maybe we will take roughly 3 lectures. After that, we divide this into 2 parts. The remaining lectures are divided into 2 parts. In part 1 of this part 2, that is what in part 1 we study basically elliptic equations, Here you will see the existence, uniqueness, regularity. These are the 3 important concepts for the well posedness of the formula, regularity. And before that, basically we will also regularity all the study, we study these equations in the abstract formulation, abstract weak formulation. So, it is going to study, it is not a classical theory, it is a formulation in the weak sense, abstract weak formulation. And in the you will also see what are called Stambakia theorem, Lax-Milgram theorem and all that, the minimization problems associated with it, Lax-Milgram, Stambakia. And we elliptic equations, probably if we have time we will also study the Stokes system, if you get it, at least in the linear setup, Stokes system. And then we study some spectral problems, that means eigenvalue problems. And Rayleigh question, the characterization of the eigenvalues quotient. Okay. And then we will see as we go along, and these things we plan to cover probably around 16 lectures, that means around 8 hours. not 8 hours, not 16 lectures, we may not get that much, maybe 14 lectures, 7 hours. In the part 2, the basic thing, elliptic equation, here we will study evolution equations. So, to study this, one of the basic ingredient in addition to Sobolev spaces etc., what we require what is called a semi group theory. So, we will give a brief course on semi group theory. You will see theory, you will see Healy, Yoshida, Phillips and other theorem, especially the aim is to introduce come up to Healy, Yoshida. Okay. Perhaps we spend around 7 to 8 lectures or something, maybe less or more, you will see maybe 4 hours. And then we use the semi group theory to formulate evolution problems. Evolution problems in the sense of abstract operator equations, abstract operator equations. Basically, it's an ODE in infinite dimensional spaces, in infinite dimensional spaces, infinite dimensions. Something of the form du by dt plus AU. You know that when A is a matrix, it is a finite dimensional du by dt equal to 0 or f, whatever it is. Okay. So, when A is an integer or A is a real number or A is an matrix, n by n matrix is nothing but your ODE system in Rn. But for the PDE, eventually you convert your PDE into an evolution ODE form in infinite dimension, appropriate Hilbert spaces given by the Sobolev spaces here. So, we at least we try to cover the heat equation, wave equation, and Schrodinger equation. At least these things will be covering Schrodinger equation, and if time permits more about it, depending. And these things we maybe try to finish it in the remaining 20 remaining of the 20 lectures, roughly 12 lectures or something like that, 12 lecture to 6 hours. Okay. And that is the plan of this course. So, the part 1 and part 2 of the course, advanced PDE course, is cover a 1 semester course. So, let us go to the next one. Okay. So, now let us do some here also basically you will be studying using these equations formulation in appropriate spaces. You study existence, uniqueness, regularity and various aspects associated with any PDE theory. Okay. So, let us go to review of Sobolev spaces quickly, which you have already studied, review of Sobolev spaces. If not, please go through our first part of the course, Sobolev spaces. So, let us typically omega subset of Rn, so I am recalling this, open, in general need not be bounded, but most of the time we may assume boundedness. But to define bounded, not always, okay. To define you do not need boundedness, but many results you may need boundedness. Okay. So, the spaces can be defined that way. So, the for 1 less than or equal to p, I will restrict only to the case p equal to 2. So, most of the time we will be using only p equal to 2, but let me give the Sobolev spaces. Let me recall the space W1 p of omega. In fact, you can define Wm p of omega. Wm, p represents the growth, m represents the number of derivatives. Okay. M equal to 0, 1, 2, 3. Okay. So, this is less set of all f in Lp of omega such that your all derivatives derivative of f, so otherwise let me use u only, such that is in Lp of omega, this is for all derivatives up to order m. Okay. This is the distributional derivative, keep that in mind. Distributional derivative visualized as a function. So, distribution derivatives of an Lp function need not be function, but you are demanding that it is a function and that belongs to L2, and you can write your norm which is a Banach space, and the norm is given by norm u at W1p, and sometimes this is also written like this. So, various notations according to the convenience we will be using it. Okay. Is equal to, you take all its derivatives, take its norm at Lp norm basically p power, and then you take 1 over p. This is mod alpha less than or equal to m. Okay. So, this is of course, this is formula is true when p equal to not true, you cannot write the power infinity, L infinity is so when p equal to infinity use the essential. So, when p equal to infinity use supernova, use essential supernova. Okay. That is all you have to here instead of that. So, you have to use the essential supernova. Okay. When m equal to 0, by convention, that means when m equal to 0, convention W, yeah, this is m here, m here, W m p. Okay. M p. Okay. So, you use that now. Convention W0 p is nothing but Lp, and most of the time we will use the case when p equal to 2. When p equal to 2, that is W2p is now p equal to 2. So, the notation is here equal to 2, m2 is denoted by Hm of omega, and these are Hilbert spaces, and you have your inner product uv in Hm, inner product is nothing but integral over omega t power alpha of u, t power alpha of v, and you sum it over all mod alpha less than or equal to m. Okay. So, that is the inner product it will be doing it, and these are Hilbert spaces, we do that one. Now, let me make some results. So, as I said, it is only a review, so I will not be proving anything. One of the important thing is we know d omega, the space of C infinity functions with the compact support is dense in LP. So, as far as the Hilbert and Banach spaces and separability, reflexivity, it exactly follows what is true in LP. But one important result about the density, which does not follow that easily, dense in LP of omega, but in general d omega is not dense in WMP. Okay. But one case which you know is d of Rn, when the space is a full space, is dense in. All these results should be known to you because it is repeatedly using it, dense in WMP of Rn. So, I will state a few results regarding the density later. So, this motivates us to define a definition, because d of omega is not dense in. So, we denote it as a new space H1 naught of omega is the dense, the completion of omega, closure of d of omega in HM. In fact, you can define HM. Okay. You can do this process even for the all other LP and WMT. As I said, let me restrict only to HM, because these are the spaces you will be using for our study. Okay. For there are the use of WMP in other spaces, but let me restrict myself to here. Okay. This is in WM of omega. Indeed, this is also a Hilbert space, and this is of course contained in HM of omega. And what we are telling is that this tells you that HM naught of Rn is equal to HM of Rn. So, you have, that is all trying to say that. So, there are, so it is important to have the density results, because many times when you do the calculations, you basically has to do the calculations using the smooth functions, and then use the density argument to results, prove the results in general. So, there is another interesting space, you see that it is H minus 1 of omega, that is nothing but the dual of HM naught of omega. Okay. So, it is a dual space. This dual space is also important. You can define H minus m of omega. Okay. So, you have dual space of H1 HM naught of omega. Okay. In particular, you have H minus 1. This will be using we will be using a lot. So, H1 naught of omega prime. So, with this kind of definition, so if you take the dual of HM, you may not get what we are supposed to get. This structure of inclusion is happen. So, if you have your L2 here, L2 of omega, this is nothing but your H0 of omega, and this contained in H1 here is a H1 naught of omega. It is all continuous embeddings. So, you will get HM naught of omega like that, a continuous inclusion, and this inclusion follows here. Here you have H minus 1 of, these are all we have discussed it already here. Okay. So, H minus 1 of omega goes like that, H minus m of omega like that. Okay. And this structure you get it. Okay. So, you have that inclusion. Note that these spaces are not function spaces, these are all dual spaces. Okay. So, what else you want to say? So, we have this one of the triplet which you will be using it in our analysis, triplet. This triplet, so you have your L2, this is will be using, here you will have your H1 naught, and then you here you will have H1, H minus 1. So, this triplet so you have an interesting triplet which you will see during our study L2. It works as a, for any spaces you can define like that, a triplet, and this is interesting is H1 naught prime. So, you have this triplet, use of these triplets. Okay. And you also have a, which I will discuss maybe a little later, H1 naught of omega embedded in L2 in the sense of compact, okay, if omega bounded. Okay. If omega bounded. So, in sense in the what do you mean by an injection? So, this is just a maybe a knot which we already discussed in detail. Suppose x contained in y and the injection I from x to y, the identity mapping is continuous, we say x is embedded in y continuously, embedded in y continuously, and which we denote by x embedded in y. If the embedding is compact, if the embedding is compact, that means the identity is compact operator, embedding is compact, we say it is embedded compactly, then we denote this notation. This is our notations which we want to use it H1 naught. In this sense, you can embed this space. This is very useful. Again, we will be using that space of embedding. In fact, H1 smoothness, etc. In fact, we will be using this embedding in the study of existence in uniqueness, which we will be doing it. And let me do a couple of things more before ending this lecture. And when omega equal to Rn, we have a, you can define, you can characterize Hm of Rn via Fourier transform. Okay. How do you do? So, you have, and in fact you can define Hs for any s. For any s, that is advantage. For any s belongs to R, you can define Hs of Rn as the set of all Tambert distributions. This is the Tambert distributions. For the Tambert distributions, you have the Fourier transform. So, you demand this 1 plus mod psi square whole power s by 2 u hat is in L2 of Rn. Okay. So, note that these are Tambert distributions. Tambert distributions, and the is the dual of dual of zeta of Rn, zeta of Rn. In fact, this is a special class of distribution. Those distributions, the distributions are defined on d omega, but those distributions which can be extended to the Schwarz class, then not that everything can be extended. Okay, those distributions which can be extended to a bigger space called this Schwarz space, the basically a rapidly decreasing functions Schwarz space. And the Fourier transform on Schwarz space is a kind of an isomorphism. When you take Fourier transform of Schwarz function, it will become a Schwarz space which can be used to define for every Tempel distributions, and the Fourier transform will remain there as Tempel distribution. So, so with this can be you can define the norm also. Norm u in Hs of Rn is nothing but the norm of it is in L2 1 plus mod psi square S by 2 u hat is in L2 of R. So, you may ask a question, when S equal to m, an integer, positive integer, not only a positive integer, when S equal to m is a integer both positive and negative, your Hs is already defined. Will this will be different? No, it will be the same thing. When all this requires a proof. Okay. When S equal to m greater than or equal to 0 integer, Hs coincides with the earlier definition. Hs of Rn is the same as the previous definition basically. Similarly, when S equal to minus m, m greater than or equal to 0 integer, so this gives you a direct definition of h minus 1, then this become h minus m, h coincides with Rn, coincides because the dual of that, because Hm naught of Rn as a dual we have defined. Now, we have the same thing, it is coincides. Of course, this is the first one is not difficult to prove, but the second one requires a proof based on proof by Fourier transform. So, which requires a proof basically by Fourier transform. Of course, I am not going to do that here. Okay. And as I said, zeta of Rn is the source space, which is the space of a function, and it is rapidly decreasing, things like that. So, before the second lecture, let me do one more thing and then I will finish it. So, what we are going to now in the couple of lectures of the review to discuss few issues. So, there are 4 issues which we already seen in the 4 issues. As far as there are many issues, there are 4 important issues as far as Sobolev spaces are concerned. All this we have seen it. Sobolev spaces are concerned. Okay. So, what are the 4 things? One is what are called the prolongation. I will a few things I will tell you. This also called extensions. And then density results, which I already mentioned, density results. And the third one, as far as the boundary value problems are concerned, what are called boundary values. How do you interpret the boundary values? Boundary values These are known as trace theorems. So, these three we will discuss in our review. In the fourth one is about embedding results. I will, as I said, I will little more I will elaborate on that. Embedding results, we will discuss it together with some of the important inequalities, like inequalities like Poincare, Poincare-Oettinger, how much we do not know. Let us see Poincare, Oettinger, maybe if you get the time, Cohn's inequality is important. Study the elasticity system inequality. So, this part after the review article in the as these things will be discussed little more details about that one. So, we will finish this first lecture and then we will continue about the review about all these issues, prolongations, densities, just to recall. So, if you want to study and if you want to write your examinations, it is better that you review these things thoroughly, including the proofs which I will not be giving. Thank you.